So, for today, we will be talking about velocity and acceleration and their relationships with derivatives and integrals. And just a little side note, I'm at 99 subs right now. Man, oh my god. First three digits. That's absolutely crazy. So I appreciate all of you that watch my videos. Or maybe there's not a single person that consistently watches my videos, but the 99 subs is still pretty exciting for someone that just started YouTube. So, let's start this off. We're going to be associating, position. So x is your position variable, v is your velocity, and a is acceleration. So let's write that down. This is position, this is velocity, and this is acceleration. Acceleration. And I'm just going to let you know that your velocity, your instantaneous velocity, which is the derivative of position over time. So what I mean by position over time is just if you had a graph with two variables, position and time. Time would be on the x-axis and position would be on the y-axis. So hence the top variable is the y-axis variable and the bottom variable is the x-axis variable of your graph, and you would find the derivative of this graph to get your instantaneous velocity. And instantaneous acceleration is the derivative of velocity over, I wrote that really big, derivative of velocity over derivative of time. So again, if you had some graph, maybe one that looked like this. If you had a graph, the x-axis would be time and the y-axis would be velocity. And if you found the derivative of any point on this graph, you would get your instantaneous, so this would be the instantaneous acceleration. Now, how about integrals? Well, the integral of velocity as some function of time is equal to your change in position. So change in position, it's not your actual position. And your integral of acceleration with respect to time is equal to change in velocity. So these are really important things to know. And on just a quick review, whenever you are speeding up, your velocity is either positive and your acceleration is also positive, or velocity is negative and acceleration is also negative. When you are slowing down, it can be vice versa. The reason why I'm reviewing this for you guys is because in the problems this will be important. So your velocity is negative, acceleration is positive, or your velocity is positive and your acceleration is negative. In this problem, we have a graph, velocity, and time, and I have your relationships written down here. So we have 4 questions that we have to solve. The first one is, when is the object at rest? Well, this is a graph of velocity over time. So when the object is at rest, that means that we have a velocity of 0 meters per second. Therefore, there is only a couple points where the object is at rest. It's at rest here, which is, the 1 is actually covered at 1 second. So part A, let's write this with part A actually. Part A, B, C, and D. That's not a dot. D. So part A, the object is at rest exactly at 1 second and from 3 seconds to 4 seconds. So that was an easy one. How about, when is the object speeding up and slowing down? So the object is speeding up when both the velocity and the acceleration have the same sign. So they're both positive or negative. And keep in mind, this is just the velocity graph, but we can actually extrapolate. That's not the right word for. We can get the data, or we can get the acceleration based off of the derivative of this. So remember what I said about dv over dt? If you were to find the derivative of some graph dv over dt, then wait, that was wrong. Not some graph of velocity over time, then you would get the instantaneous acceleration. So Let's solve for that. When is the object speeding up and slowing down? Well, the acceleration is pretty much constant along these straight lines, since the derivative is the slope of this. So from 0 to 2, so from 0 to, let's use a different color, from 0 to 2, 0 to 2, the acceleration is negative because the slope is going down. How about from 2 to 3? Well, it's positive. From 3 to 4, well, the velocity is not moving, so we have a 0 acceleration. So acceleration is 0. And the slope here is also positive. And we also have a 0 acceleration here because the velocity is not moving. Now, all we have to do is look at the points in which velocity and acceleration are or have the same sign. Well, from 0 to 1, velocity is positive. So from 0 to 1, velocity is positive, and acceleration is negative. Therefore, from 0 to 1, our object is, let's write speed, let's write a little graph, speeding and slowing. Our object from 0 to 1 is slowing down. 0 to 1 is slowing down. Okay, how about from 1 to 2? Well, 1 to 2, your object has a negative velocity, and your acceleration is also negative here. Therefore, from 1 to 2, your object is speeding up. Okay, how about from 2 to 3? Well, 2 to 3, your velocity is negative, and your acceleration is positive, so the object is slowing down from 2 to 3. How about from 3 to 4? Velocity is 0, acceleration is 0, so it's neither speeding up or slowing down. It's just at rest. Okay, how about from 4 to 5? Well, 4 to 5, velocity is positive as it's above 0 on this graph. And acceleration is also positive. So we are speeding up from 4 to 5. And the last part, 5 to 6. Well, even though the velocity is 0, the acceleration is 0. Therefore, we are not speeding up nor slowing down. So from points 1 to 2, 0 to 1, 4 to 5, 2 to 3, that's when the object is speeding up or slowing down. Okay, let's do C. Well, C is find the displacement and the distance. So these are two different things. The displacement is the net integral. So if you want to find the integral of velocity, that will equal your displacement. So just the integral, or the net integral, is the area between the curve and the x-axis, with the areas in the negative side being treated as negative area, which isn't a real thing, but is treated as so. So your displacement takes into account. So if we were to find the area of this triangle, well, the area of this triangle here, using some triangle formula, is just 10. The area of this entire triangle is 20. And the area of this triangle is also 10. And then the area of this triangle here is 10. Wait, sorry, this is 5. This is 10. This right here is 5. So the area of this triangle in this section that's separated is 5. That blue is kind of light, but you get the point. So find the displacement. So the displacement treats negative the side below below 0 as negative. So we have 10 here, minus 20, plus 5, and plus 10. And if you do all this, well, your displacement should be just 5 meters, as the unit is meters per second for velocity, and for time it's seconds. Okay, how about the distance? Well, the distance treats all the areas as positive. So this is, let's see, this is displacement here. This is displacement. Don't like that. It's very small. Displacement. And then now we're finding distance. So distance treats the areas as all positive. So we add everything up together. We have 10 plus 20 plus 5 plus 10. And this equals to 45 meters. So your displacement is just 5 meters. So from your start point to your end point, so from point A to point B, you basically only traveled 5 meters. But the distance says that you traveled 45 meters. So you probably took some other path, walked around, and then you got to here, and the length of this path is 45 meters. Let's erase this because it's kind of blocking the way. I'll keep that in for the thumbnail. Nah, I'll make a custom thumbnail for this one. Okay, so find the average acceleration from 1 to 5 seconds. Well, the average acceleration is as so. So it's the change in velocity over the change in time. So we have our change in time. Change in time is from 1 second to 5 seconds, so this is just 4 seconds. How about change in velocity? Well, at 1 second, our velocity is, at 1 second, our velocity is 0 meters per second. And then at 5 seconds, our velocity is 10 meters per second. So our change in velocity actually is positive. So we went from 0 meters per second to 10 meters per second. So we have change in velocity is equal to 10 meters per second. And in the opposite case, if our final velocity at 5 seconds was negative 10, so some graph imaginarily went down like so, then our change in velocity would have been negative. But it's positive in this case. I just wanted to cover all bases to make sure I don't cause any confusion for future problems. So we write change in velocity over change in time. So we change in velocity is 10 meters per second, 10 meters per second, and change in time is 4 seconds. So we divide 10 divided by 4. This is 2.5 meters per second squared as the average acceleration. Now you have a position over time graph. So you're going to have to use some double derivatives to interpret your acceleration, but I encourage all of you guys, for every single question I post out there, to try it out first for yourself, and then whenever you get stuck, it's fine to watch the video. But let's do the first part. So the first part is just find the displacement. Well, we don't have to find any integrals or anything like that. Last problem, we had to find some integrals to find your displacement. But for this, you don't have to find integrals. Our position graph is right here. So the displacement would just be your initial position, which is just at 0 meters, and your final position, which is just at 20 meters. So that's all the information you need. And your displacement is simply 20 meters. So, or final position minus initial position, and that's just equal to, well, 20 minus 0 is just still 20 meters. So 20 meters is your displacement. Okay, how about when is the velocity positive or negative? Well, velocity is the derivative of position with respect to time. And we have that here. Well, we have our position variable in the y-axis, and we have our time variable in the x-axis. So this is perfect. All we need to do is find the derivative of this so we can solve for all the instantaneous velocities when they're positive. So when are the slopes positive? Well, from 1 to 2, the slope is positive. So positive, let's write positive here. Let's write negative here. So this is negative. And at positive, it's from 1 to 2. 1 to 2. And technically, your velocity is discontinuous. Your velocity graph is discontinuous. And so is your acceleration graph. So I'm going to separate all these intervals. 2 to 3 is also positive for your velocity. But from 3 to 4, your slope is negative. And exactly 3, your velocity is actually 0. Because the tangent line is just horizontal. But from 3 to 4, your velocity is negative. And from 4 to 5, your velocity is positive because the slope is positive. So from 4 to 5, positive, and the negatives are from 0 to 1. Because the slope is negative from 0 to 1, and we already said that 3 to 4 is negative as well. And how about your velocity from 5 to 6? Well, your position quite literally stays the same. Therefore, your velocity is at 0. At 0 from 5 to 6. I guess I can write 0. 0 from 5 to 6. Okay, how about the average acceleration? Now, this is the hard part. So, the average acceleration, or the acceleration, is solved by the average acceleration I wrote in the previous problem, but it's the change in velocity over the change in time. So, your average acceleration is just when your change in velocity and over change of time. Oh my god, what am I saying? I'm thinking about problem D right now. Okay, let's go back. Average acceleration is equal to change in velocity over change of time. So we need to solve for the average acceleration from 0 seconds to 6 seconds. Well, the instantaneous velocity, I guess this isn't technically sound, but at 0 seconds there's no instantaneous velocity. But we can say that because that's when the graph literally just starts. That's why there's no instantaneous velocity. But let's say that the slope here is negative 20. So the slope here is negative 20 meters per second. And that's because you drop down negative 20 in, well, you drop down 20 meters. Oh, this is negative. Oh my god. You drop down 20 meters in 1 second. Oh my god, I messed up the negative there. I'll edit that in when I edit the video. And also, your final velocity is just, well, this is non-moving, so this is 0 meters per second. Hence a horizontal tangent line. So your change in velocity goes from negative 20 to 0. Therefore, change in velocity is equal to 20 meters per second. Okay, how about your change in time? Well, your change in time is just 6 seconds, because you go from 0 seconds to 6. So all we have to do is do 20. Let's make space down here. 20 meters per second over 6 seconds, and that's equal to 10 over 3 meters per second squared, which is also equal to 3.3 repeating meters per second squared if you turn it into a decimal. Okay, part D. When is the acceleration 0? Well, the acceleration is 0 when your velocities are constant. So what does that mean? Well, your acceleration is, let's write it down. A is 0 when v is constant. So in this interpretation of this graph, your velocity is constant when the slope is just constant. There are many points when the slope are just constant. From 0 to 1, the slope is always negative 20. The instantaneous velocity, or the instantaneous velocity, or the derivative is always negative 20 here. Therefore, from 0 to 1, your acceleration is 0. Velocity is unmoving, therefore acceleration is unmoving. Okay, how about from 1 to 2? Well, velocity is always 20 meters per second in this case. It's a straight line. Therefore, your acceleration is also 0 from 1 to 2. Okay, how about from 2 to 3? Well, here's this. Your tangent line, or your derivative, is constantly changing on this curve. I can draw them all out for you, but there's infinitely many. So from 2 to 4, your accelerations aren't 0. Too cluttery. Your accelerations aren't 0. So 2 to 4 is not going to be the answer for this problem. Okay, how about from 4 to 5? Slope is constant, therefore acceleration is constant. So from 4 to 5, acceleration is 0. And from 5 to 6, well, then again, 5 to 6 also has a constant velocity of just 0 meters per second. So our acceleration is 0 there. So if you understand derivatives and integrals well enough, then acceleration and velocity isn't too hard for you, because they're just relationships of derivatives and integrals. So on the final note, if you have any questions, put it down in the comment section.